Pow. Good morning, Astronomy 1020. Welcome to our last lecture before the exam on Tuesday. I want to make sure that I remind you guys that the exam is on Tuesday and we got to take that serious. It's one of the 2 times that we just need to be here and give it our all. Today's class, you're going to have a 3rd lecture on the sun. I've really indulged in the sun this semester so that we could go through it with painstaking, lovingly detail. And after our lecture on the sun, we're of course going to do our exam review session instead of a homework today. And I think that ought to really help you guys. I did this with my Astronomy 1010 class yesterday, and we worked through a whole bunch of problems that are almost identical to the ones that are going to be on the test. It'll give you guys a chance to try to do some of these problems without me kind of shepherding you through it. So you'll have to kind of do it on your own. And then I will explain how to do it so you guys can sort of go through that process and learn. It'll probably make more sense once we're doing it. Okay, so unless there are any other questions, I am going to get back into it. I believe that in our last lecture, we left off on sunspots. Is that correct? Stacy gives me the thumbs up. Actually, hold on. Let me hide the video trolls here because they're distracting me from seeing the faces of the humans who interact with me. Okay, so what can you tell me about sunspots? What have you learned so far? Okay, let's start with a simple and more directed question. On what layer of the sun do we find sunspots?
Photosphere.
The photosphere, that's right. So sunspots are found on the photosphere. I wasn't planning on making this a note, but I should mention that the first astronomer who observed sunspots in the 1600s was Galileo Galilei. He built the first telescope for astronomical observations, and he ended up losing his eyesight. He went blind from staring at sunspots with his naked eye through a telescope. One of the first rules of telescope observations is don't point it at the sun, okay? Because you can literally melt your eyeball inside of your skull. Today, we can look at the sun with protective shields. Did I show you guys that solar filter last time? It looked like a piece of tinfoil. Yeah. So that's how we observe sunspots today. We can use these solar shields that allow us to sort of study them. And as you saw in your lab on Tuesday, you can actually do useful things with sunspots, like you can measure the differential rotation of the sun. I don't know if we got into the cause of sunspots. Did we? Do you guys remember what causes sunspots? Well, what's the typical size of a sunspot? Do you guys remember that at the beginning of this lecture sequence on the sun, we actually estimated the size of one of them? No? Yeah, at least the size are bigger than the Earth. So they can be comparable to the radius of Earth or more sometimes. And the cause...
Is it solar flares?
It's not solar flares, although it's related to the same processes that cause solar flares. I think when I was trying to describe the cause, I was kind of rushed. We were at the end of class, so I wasn't. They're regions of cooler plasma, okay, but what are they caused by?
They're trapped by magnetic fields, right?
That's right. Regions of cooler plasma that are trapped by magnetic fields. Normally, I'm only supposed to take 2 lectures for each chapter, but because the sun has so much rich detail, and because I think it's kind of cool, I decided to go a little nuts and spend an extra lecture on it. that means I can kind of talk to you guys about some esoteric things that I find fun. Let's go over to our slideshow for a second here. Of course, you can see pictures of sunspots here. But what I want to do is I want to show you guys how we know that sunspots are caused by magnetic fields. You guys may remember, the slides are a little bit further down here. Here's a picture of the corona shown in X-rays. So the following image here is, this is all Bremsstrahlung radiation. But the reason I want to start with this picture is to show you that magnetic fields coming out of the surface of the sun, they terminate down here at the photosphere. And this region here and this region here, that's where we're going to find our sunspots, right at the base of that horseshoe magnetic field. You'll remember that I mentioned that sunspots come in pairs. Usually there's a North Pole sunspot and there's a South Pole sunspot. So they have like a North and a South Pole side to them. Let's take a look at a picture of a sunspot up close. Now, there's a lot going on in this picture. And in a few moments, once I'm done talking about sunspots, do you guys see this mottled pattern here that looks like it was made with an artist sponge? These little tiny microspots are called granules. And the granulation of the sun on the photosphere is kind of a big deal. So I haven't actually told you what a granule is yet, but I will in a minute. Notice that sunspots are much bigger than the little granules. So typically, the way this works is this is a region of normal photosphere, and its temperature would be 5,800 Kelvin. Remember, that's the key temperature that we associate with the surface of the sun. The sunspots are usually a cooler region. They might be 4,000 Kelvin, or they might be even as low as 3,500 Kelvin. And we'll analyze what that means in just a second. I actually may give you a test question, wink, wink, nudge, nudge, comparing the two different radiation profiles of the photosphere versus the sunspot. So this will be useful for your upcoming exam. You guys will remember that when we study light, we can study absorption lines. And here I'm going to need to borrow from my lecture on light. So just a moment here. Here's a picture of the hydrogen atom shown in emission and absorption. Remember that in chapter 5, we learned that atoms produce key emission lines when electrons drop from high orbit to low orbit. This is the emission line called hydrogen alpha. But hydrogen alpha can also be seen in absorption when light passes through a hydrogen atom. If a cold electron goes from a low orbit and jumps up to a high orbit, it will absorb a photon and remove it from the spectrum. This is called an absorption line. This assumes that the atom is just chilling in space and it's not being messed with. But here's the next layer of the story. In the presence of a powerful magnetic field, you actually split the energy levels of atoms into what are called hyperfine states. And you create something called the Zeeman effect. The Zeeman effect happens where instead of getting one energy level, you split an atom's energy level into 3 little micro energy levels. And it can cause this kind of weird trident shape in the absorption spectrum. This probably sounds a little techie, and it is, but I've decided to talk to you guys about it today. This thing is called the Zeeman effect, and I want to show you an example of the Zeeman effect right here. Function F581. Okay, here you can see the actual picture of the sun. And this little dark line that you see there, that is the slit of the spectrograph that we're using to analyze light from the sun. Normally, when the line covers a normal portion of the sun's photosphere, you see a single dark absorption line. But check this out. Do you see how when the line goes over the sunspot, you can see the absorption line split into this little trident shape? That's called the Zeeman effect. It's something you usually learn about in graduate school. And you can actually measure the width of this trident, and it can help you estimate the strength of the magnetic field. Okay, you're probably going to forget all that, but what's the point? The point is sunspots are caused by magnetic fields. You guys will remember that one of our rules for magnetic fields is that magnetic fields trap plasma, okay? So let's do a little analysis on how this works. Bust out your calculators, and let's do a sunspot analysis. Okay, so let's take a square, a little square representing a patch of the sun. And here's our sunspot. Remember that the reason, I'm sorry, I'm just checking out the chat log here. The weird light thing that only happens when you don't observe it. Well, you're talking about the Heisenberg uncertainty principle, I think, and it's related in a very vague way, but not too directly. By the way, normally at the photosphere of the sun, so here's the photosphere, light is shining into space. So here's visible light coming from the photosphere. And you guys will remember the photosphere glows like a black body. A black body means I glow because I'm hot. And normally the photosphere is bubbling kind of like a pot of soup. When magnetic fields trap a sunspot, they prevent gas from sinking back down into the sun. And so that little pocket of gas which is trapped there continues to radiate away its energy, kind of like a potato getting cold on a windowsill or something. And eventually the bubble becomes so cool that it starts to appear dark by comparison. So this part of the photosphere is maybe 5,800 Kelvin. And this part of the photosphere we'll say is maybe 3,500 Kelvin. Okay, let's do a comparison. I want to ask you guys two questions, and these could be questions that appear on the test. Actually, I'm going to give it a little nudge because I'm going to make it 4,000 Kelvin. Usually it's about 1,000 Kelvin cooler, sometimes 1,500. Okay, the first question I want to ask is, how much more light does the photosphere, I shouldn't use any abbreviations, so that's going to confuse you. How much more light does the photosphere emit? And then question number 2 is to compare peak wavelengths. Would you guys be able to look at your formula sheet and know what formula you need to answer question number 1? You guys want to give that a try? I can't speak today. I'm not doing it well. Which formula do I want to answer question 1? Someone talk to me today. Blair says she couldn't open the, Jesus, there's always a problem here. Blair, did I email it to the class? Class, did I email you the, okay. So let's do that then. Meanwhile, the rest of you who did get the formula sheet, oh God, this is going to be a mess. I'm going to email the class the formula sheet. Shoot, where the hell did Blackboard go? Where is Blackboard? Okay, there we go. Get out of here. Okay, I'm going to email the class the astronomy AS1020 midterm formula sheet. Okay, formula sheet. Attach file. It's in my Dropbox. Bear with me, guys. Exams 1020 formula sheet. All right. Yeah. Okay. Check your email, Blair. You should see the formula sheet, and that goes for anyone else as well. So have you guys worked out which formula you're going to need?
Is this C equals wavelength times F?
I'm afraid not, Arunsak. That formula relates the wavelength of light to the frequency of light. But here I'm asking you about a quantity of light. Do you guys know what parameter measures quantity of light?
Brightness.
Thank you, Christopher, for the win. Christopher,
Um,
I'm asking you to find the brightness. Very good. Christopher, which formula would allow us to calculate the brightness from the given temperatures?
Weins law?
Wein is going to give you question 2. So this is what you're going to have to do during the exam. You're going to have to be able to pick a formula based on the question. There's only a couple of formulas that involve brightness, B.
Boltzmann.
Yeah, Emily. Very good, Emily. This is the Stefan Boltzmann law. Very good. Very good. Okay, I'm going to erase this so we can do the calculation. So let's first do the Stefan Boltzmann law for a sunspot versus the photosphere. It feels really dark in here. Let me turn my lights up. Okay. Okay, so remember the sunspot's at 4,000 Kelvin. Okay. All right, so first we'll do the photosphere. The brightness, sigma times T to the 4th. Sigma is the Stefan Boltzmann constant, which is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th, times the temperature, 5,800 Kelvin to the 4th power. Okay, class, you know how to take your 4th power, right? I'm sure you all know how to take a 4th power, don't you? Alejandra, what's the key?
Is it the XY key?
That's right. Okay, punch them up. Punch them up. Hey, shouldn't you be at the vegetable market?
No, I'm gonna go later at 3.
Oh, okay. I'm so glad you could join us today. That's nice.
I got 67.9 times 10 to the 6. So
Oh, I like your
67
styles.
million,
So you basically got 68 million, right?
pretty much.
That's cool. Hey, Arunsak, I really like your style. I like how you put that into millions. What are my units?
Watts over meter squared.
That's right. Sorry, I didn't put these units in blue. I got screwed up there. So 60, I don't like how smushy this is here. So for the photosphere, you got 68 million watts per meter squared. Okay, now let's do it for a sunspot. For a sunspot, we have the brightness equals 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th times 4,000 Kelvin. Actually, guys, can I tell you something? We're doing it wrong. You know how we could have done this a lot cleaner and a lot neater? With a proportionality argument. I've got a better idea. I'm going to show you guys some advanced techniques here. If it's true that brightness is equal to sigma t to the fourth, remember that sigma is a constant. So I could write brightness is proportional to the fourth power of temperature, where I've used that proportionality symbol that we used in the gravitational law. Therefore, if I just want to start by taking the ratio, the brightness of the photosphere divided by the brightness of the spot should be equal to the ratio of the temperature of the photosphere to the fourth power divided by the temperature of the spot to the fourth power. Did that make sense to you guys, or was that too advanced of an argument for you? Arunsak, did you follow that? I'm just gonna, no, you didn't follow that? Christopher?
It would help if you repeated it like one more time.
Sure.
It's a little bit hard.
I shouldn't have distracted you with the proportionality argument. One more time. Okay. You guys agree that this is the formula. Brightness is equal to sigma temperature to the fourth. And at first, I started having you guys do it in a very mechanical way, where I asked you calculate the brightness of the photosphere, then calculate the brightness of the spot. And then I was going to have you take the ratio to see how much more light comes from the photosphere than the spot. And then I started thinking maybe I should show you guys how it's better to do it symbolically first. So on the top line, I have sigma times the temperature of the photosphere to the fourth power. And on the bottom, I have sigma times temperature of the spot to the fourth power. And because the Stefan-Boltzmann constant is going to be the same both times, the Stefan-Boltzmann constant cancels out. And I end up that the ratio of their brightnesses is the ratio of the two temperatures to the fourth power. Honestly, I thought I was going to be able to say that like cleaner and simpler, but I'm worried it was too many words. Did it make any more sense this time, Arunsak, or was it just as confusing? Oh, okay. So I think it
Made more
helped.
sense.
I think it helped if I put the Stefan-Boltzmann constant in first and then canceled it out. Okay, watch this slick Rick technique from math. I'm going to factor out the fourth power. So I'll just simply get the ratio of the temperatures. Oh, sorry. Temperature of the photosphere divided by the temperature of the spot, all to the fourth power. Now that was many words. I probably shouldn't have even tried this, but now I can calculate the ratio of brightnesses, the ratio of the photosphere. God damn it. My handwriting's not good today. The ratio of the photosphere brightness to the ratio of the spot brightness would be 5,800 Kelvin divided by 4,000 Kelvin, all to the power of 4. Divide them, then raise to the fourth power. Tell me what you get. Actually, let's do it together. Oh, okay. Run sec right there. 5,800 divided by 4,000. To the power of 4 is, yeah. Arunsak, what is the meaning of the 4.4?
The photosphere is 4.4 times hotter.
Not hotter. It's clearly not 4 times hotter. It's only a little bit hotter. Times brighter, says Cameron. Cameron saved us there. It's
Shout out Cameron.
4 times brighter than the spot, right? In other words, Arunsak, let's make sure we can bring this back to picture land. In other words, you're getting 4 times as much light from this patch of sun as you are from this patch of sun, right? Let's also analyze their peak wavelength, and then I'm going to make a cool point, okay? So first, let's find the peak wavelength of the photosphere. Wien's law tells us the peak wavelength can be calculated by 3 million nanometer kelvins divided by the temperature T. So if you plug in 5800 Kelvin, what do you get?
$517.
Chris, let's just round it to 520. What are the units?
Second.
I'm sorry?
Nanometers.
Thank you. Did you guys just phase out there? I lost you guys. You phased out of the space-time continuum. All right. I'm already having a very frustrating day here. Everything is awkward and weird. Hopefully that recording is still preserved. Yes, Arunsak, nanometers. Thank you, sir. Thank you. Okay. Yeah, actually, Devin, I don't have any T in my hand, and that's exactly what's going on. So we're going to take care of that T problem right away. In what regime of the electromagnetic spectrum is 520 nanometers found?
Oh no, continuous, right?
You said it right the first time. Visible.
Visible, yeah.
What color is it?
So somewhere in the red.
False.
Indigo.
Also false.
Yeah.
Do we need the cheat sheet?
Cheat sheet, please.
Okay, cheat sheet.
Yellow?
No, not exactly. You're getting closer. I want you guys to actually memorize the colors of the EM spectrum. Hold on, let me find it here. I kind of want you to memorize this sort of by accident without trying. What color is 520 nanometers?
Green.
Green. Wicked, wicked, wicked green. Okay. So this is visible, and the color is green. Okay, now let's try to do it for a sunspot. What is the peak wavelength of emission? It's 3 million nanometer kelvins divided by 4,000 Kelvin.
750.
Units?
Nanometers.
Regime of the electromagnetic spectrum?
Visible.
Color?
Red.
Yes.
Let's go.
Now you guys are talking. Okay. That took a little bit of time, but I'm building up towards a legendary question. A question that astronomy professors love to ask of their students. I want you to think about everything you just learned about the 4.4 times brightness. I want you to think about the green versus the red. And I want you to look at a picture of the sun with sunspots. Let's go to slide 3. Let's go to this slide. Okay. Suppose the sun were covered in one big giant sunspot. What color would the sun be? What would the sun look like if it was covered in one big fat giant sunspot?
I'd guess red. Towards red, like reddish in that area.
Well, at
Purple.
least, Christopher, you didn't say black. There's multiple wrong answers to this question. The first wrong answer is black. If you covered the sun in a sunspot, it would not be black. Oh, Cameron has the right answer. Oh, Blair, you said black. I don't even speak your like Gen Z LOL shit, so I don't know what zoned means. I don't even understand that. Anyways, okay. Okay, Cameron got the really right answer, okay? If you were to cover the sun in one big giant sunspot, the sun would pretty much look exactly the same. It would be probably a little redder. Christopher wasn't exactly wrong, but it would not be red. Why not?
Is it because it would still be a black body?
Exactly. Exactly. Hold on. Hold on a second. Can I show you guys another 4,000 Kelvin black body while I'm at it? This is a 4,000 Kelvin black body right here. Let's plug it in. I know you're seeing it through the camera and all. What color is that?
It is
white.
white with some red.
Yeah, actually, this is the nuance. Who said that? Who was just talking to me there? Who said it's with some red?
Farmer Alejandra.
Oh, Alejandra, thank you. Alejandra, if you think about it, an incandescent bulb does have kind of a red rosy glow, right? It's more on the reddy or orange side. It's still white, but it's got this kind of red glow to it. Absolutely. In fact, if we were to look at the radiation profile of a sunspot, we would see somewhere over here. I don't know if it's slide 68. I have a plot of, here's a good example. So light from the photosphere probably peaks in the middle of the visible. So you get roughly equals amounts of red and blue with a lot more green and yellow. And that creates a very pure white. But the sunspot is kind of more like this thing over here, where it peaks just past the red. So you're still getting white because you're mixing all these colors together, but it's kind of a rosier, reddishy, orangey white. So Christopher, if you think about it, the sun today from Earth actually looks kind of yellowish. So I bet, Christopher, that if the sun was 4,000 Kelvin, it actually would look a bit more reddish in our sky. But from outer space, it would probably still appear white. Okay, so now I'm going to ask the next level question. You guys actually did pretty admirable in that question, better than I thought. Why do the sunspots look black in the photographs then? And why do they look black when I look at them through my telescope? Well, besides Austin, you're just a mean old troll today. Anyways, why do the sunspots look black? Because they're cooler. Okay, yep.
I want to guess that it's because relative to the rest of the sun, they're not quite as bright.
Right. So actually, Christopher, you said that very well. You know how I would put it? It's a contrast issue. It's a contrast in photography issue. Like, I don't know if any of you guys have any experience taking photographs, but if you guys have like a big DSLR camera, you can change your aperture and your exposure rate, right? Suppose we change the exposure rate to let the sunspots are not black. They're actually giving off light. They look black by contrast because you're getting 4 times more light from the photosphere than you are from the spot. Okay, I've gone on a little bit long on this here, but in any case, other things that you should probably know, creepy things about sunspots, okay? We've been studying sunspots since the time of Galileo, and I want to show you guys something. This slide here, function F583, this is a plot of sunspot observations from the first observations of sunspots taken by Galileo in the early 1600s, all the way up to roughly 2000. Yeah, I like creepy too, Christopher. Okay, so What do you guys see happening here? Can you see this oscillation? What is this oscillation and what's going on there? I see lots of spots. I see few spots. Lots of spots, few spots. What's going on? Yes, Devin. Devin has it right. The 11-year solar magnetic cycle. We get a period of 5 years of sunspots followed by 5 years of no sunspots. Here's where the creepy comes in.
So,
Oh, yeah?
so what's with like the 100 years of no sunspots?
Exactly. This, my friends, is a mystery of astrophysics. It's known as the Maunder minimum. And the Maunder minimum was this weird period in the sun's history where sunspot activity in the 11-year solar magnetic cycle stopped. And we have no idea why. But it corresponded with like a mini ice age in Europe and some globally cold temperatures on Earth. There is some kind of weird connection between what was happening on the sun at the time and temperature patterns on Earth. And you actually can Wikipedia this. It's a cool read. There are all these different theories about why this might have happened, right? So if you want to, I'll just put the link in there. I don't have time to get into the whole bloody thing, Maunder minimum, but I just think it's one of the coolest things. It's a prolonged sunspot minimum from 1645 to 715. And people have all these different theories about why it is. You know, the sun took a lunch break. It did. If you think about this, guys, the sun is a structure which evolves over billions of years. If we've only been studying the sun properly with telescopes for 200 or 300 years, there could be weird changes to the solar magnetic cycle that only happen once in 1,000 years, for instance, and we wouldn't have been observing the sun for long enough to detect those. Do you see what I mean? We haven't been smart for that long. We haven't been smart enough to study the sun for just a couple of 100 years, but stars can evolve over hundreds of thousands of years, right? So who knows what kind of other strange things the sun might do from time to time. Okay. I think it's time for us to burrow into the interior of the star and learn about nuclear fusion. This is what I was looking forward to all day. So, oh yeah, Blair, let's hear your question. Actually, yeah. So Blair just brought up Earth's geomagnetic poles reversing. And if you guys did not know this, periodically, actually, I'm saying this wrong, aperiodically, Earth's north and south pole spontaneously flip, and north pole of Earth gets reversed to south pole. This is related to something called the dynamo effect. It's the way that Earth's geomagnetic field is created. But what's cool about the geomagnetic reversal, Blair, is famously the reversal of Earth's north and south poles has no periodicity. It's almost like random. Let me show you a Wikipedia page about that. Geomagnetic reversal. And they try to display it in this graph. Let me see if I can find the graph for you. Oh, the internet is slow. I really need to upgrade my internet here. I want to show you guys this. Yeah. Do you guys see this graph here? I really wanted to show this to you. So this is showing you the history of geomagnetic reversal in millions of years, starting from now up to 5 million years ago. And do you see how it goes black, white, black, white? That represents the north and south poles flipping and reversing. But there's kind of no logic to it. Like, it's not like you get 5 years of North Pole and 5 years of South Pole. You get periods of like 500,000 years of North Pole pointing up, and then like 250,000 years, and then you get these little flips here. So it's sort of a chaotic process. And today, that's another mystery of planetary science, is how and why Earth's magnetic field flips. Yes, Cameron, we can study that if we can get far enough into it. First, we got to go into the sun if you want to learn about that stuff. Okay, let's go and let's pick up a piece of ordinary photosphere. So now I'm going to dial it back a bit.
Blair still has her question.
Oh, I'm sorry. I missed the question. What was it's hard. Wait, what's the question though? Can someone translate it from chat log to me?
Yeah, so Blair had a question about why you got 3 times 10 to the 6. She did not bring up the poles. That was Chris, and you got confused.
Oh. Well, does
So
it
Blair's
matter?
question.
Okay, wait. You're asking 3 times 10 to the 6 in Wien's law then. Can you guys, all right, maybe you guys don't understand what's going on with me. It is hard for me to like go between the board and slides and thinking and talking, but also monitor the chat log. Now you guys are all Gen Z LOLers, so you love to sit there and chat your little chats, which is great, but I'm like practically a Gen X person. I like it when you talk to me like a human. So could you just translate? Are you asking about this, the 3 times 10 to the 6? Is that the question?
That's what Blair's asking, yeah.
The answer is that, well, 2.93, Blair, it doesn't freaking matter. It doesn't matter. This number comes from crazy ass physics that's over your pay grade, okay? It has to do with the black body Planck function. You're not allowed to know about that. You haven't earned the right to learn about the 3 times 10 to the 6. The 3 times 10 to the 6 is for kids. It's so that you can learn the, well, Blair, okay, Blair, I'll tell you what, here, just for you, okay? Just for you, I'm making it 2.9. If that's real important to you, it can be 2.9 from now on to the end of time, okay? And the effect it's gonna have on your answer is not even a little tiny bit. Yeah. Okay, I'm sort of teasing there, but Blair, I'd love to tell you about the 2.9 times 10 to the 6, but it would literally put you to sleep, okay? It involves like calculus and taking derivatives, and you just don't want to know. You just don't want to know. Okay, here's what you do want to know. Yeah, that's right. Blair's asking cool questions, and I want to provide cool answers. I think that's how it's done. Okay, I got to get to the interior of the sun because I have so much more cool stuff to teach you. Let's start by looking at a patch of sunlight, but this time let's forget about the sunspots. And I want you guys to imagine that I'm going to draw a little box around an ordinary patch of yellowish white sun. And what we're going to do is we're going to zoom in, and we're going to zoom in, and we're going to zoom in on an ordinary patch of photosphere. What we'll discover is that the sun at microscopic levels is covered in a fine network of granules. Granules are Texas-sized blobs of plasma that hint at the layer of the sun which sits below the surface that you can see with your eyes. This is note-taking material, so let's do it. In a way, granules are kind of like micro sunspots in that they're cooler than the surrounding plasma, but they are not caused by magnetic fields. So the photosphere is covered in a fine pattern of, wait for your $10 vocabulary word, granules. And the granules are like Texas-sized blobs of hot and cool gas that are bubbling up from the layer which is below the photosphere, which is called the convection zone. Let's learn a little bit. The granule's job is to deliver light to outer space. So here I have a hot blob. It's shining light into space. And as the hot blob shines light into space, it becomes a cool blob. And the cool blob sits next to it like so. Eventually, the cool blob sinks. Okay, let's look at a model of the interior of the star together. The convection zone spans a very, very wide fraction of the sun. So I'd say something like 1/3 of the sun's radius is convection zone, and then maybe 2/3 or another third of the sun's radius is radiation zone. In fact, so in the convection zone, which we cannot observe directly because it's too deep, it is kind of like the mantle. Like the mantle, Christopher, it transports energy by convection. The temperatures vary across the convection zone, but a representative temperature for the convection zone might be something like 100,000 Kelvin. Okay? And here, energy is transported by convection. What does convection mean? Convection means hot blobs rise, cool blobs sink. Class, what are the three modes of energy transport in nature? There are three methods by which energy is transported. What are they? No. Yeah, you're thinking of the three types of spectra. Cameron's got one of them: radiation, convection, and what's the third one? You guys don't know what I'm talking about? Daniel's got it. Convection, conduction, and radiation. Okay, so what's the difference?
So I think convection is the thing we just learned about, like how different temperatures kind of cycle around each other.
Uh-huh.
Convection is, I think, I want to say like something pulling energy into itself.
No, it's atom to atom jiggling. It's direct atom to atom contact, whereas convection is blobs being pushed around. Actually, guys, we're gonna. Sorry about that, guys. I had to do a little temperature regulation in here. I think as we dive layer by layer into the sun, I can literally feel the heat attacking me here. Okay, so we were talking about the three modes of energy transport: convection, conduction, and radiation. I want to make sure that you guys can understand the difference. A fun game to play with your friends is a game called Convection, Conduction, Radiation. Find a place where energy is being transmitted from one point to another and see if you can understand what's at work there. So let's try that game. Let's go over, here we go. Let's try whiskey on the rocks. If you have a glass of whiskey with an ice cube in it, energy is being transformed from the ice cube to the whiskey, right? Is this convection, conduction, or radiation, class?
Convection.
Unfortunately, Alejandra, no. Anyone else?
Conduction.
Conduction. And the reason why, Alejandra, is the molecules of ice are in direct contact with the molecules of whiskey. And remember that conduction is molecule to molecule jiggling. So the jiggling of the whiskey molecules crashes into the ice, and that's how it cools down. Let's try, okay, so let's try another version. What about if you're cooking a turkey in an oven? So it's Thanksgiving time. You're cooking a turkey in an oven. Convection, conduction, or radiation?
Convection.
Although there are convection ovens that have fans, Christopher, it's actually still conduction. Most ovens that cook a turkey are conduction oven, and it's the air in direct contact with the turkey. What if I take the turkey out of the oven and I put it on a windowsill, or I put it on a plate and it begins to cool over the course of Thanksgiving dinner?
Conduction.
Well, there will be conduction with the air, but I don't think that's the way it's the majority of its energy.
Convection.
Actually, to be honest, I bet if you
It's
analyze,
radiation.
yeah, infrared radiation is shining off of the bird, and that's the #1 way it cools down. This is why you can cover the turkey with tinfoil. Not only does tinfoil block visible light, but the tinfoil will block infrared radiation coming off the bird, and it will keep it. Wait, Blair, you have a turkey? When are you gonna, Blair, you need to share video and you need to share your turkey. That's awesome. Well, we want to see those turkeys, okay?
Show us the bird.
Show us the bird. So what makes convection different than conduction in radiation? Convection is blobs of gas rising and cooling. And here's an example of convection during the wintertime when you have one of these radiators. They're actually more like convectors. These slats hold pockets of air, which then heat up and they begin to rise and expand, and they displace cooler pockets of air, which sink. Convection is when you have turbulent mixing of air, like the blower that does the heating in my apartment, that central air blower, that uses convection to push hot and cold air around, okay? If we go one, by the way, in that sense, you know what? The convection zone is kind of like a lava lamp. Just like a lava lamp heats up blobs of wax and they rise to the top of the lamp and sink back down, that same cycle is happening in the convection zone. And when the blobs get to the top of the photosphere, they become what, class? What do the blobs become when they get up to the photosphere?
Granules.
Granules. Now you're with me. Okay, let's take a tiptoe down one more layer into the radiation zone. And then I want to get to the nuclear core before I run out of time. I'm going to have to shortchange the radiation zone a bit. Okay, so if we take some notes on the inner layers of the sun, we've already discussed the convection zone. Those have temperatures of around 100,000 Kelvin, and the energy transport is by convection. So far, this is just a review of the point that we just made. Now, we're going to talk about the radiation zone. In the radiation zone, temperatures inside the star become hotter, pressures become more intense, and your temperatures can easily go up to somewhere between 1 to 10 million Kelvin. That is pretty damn hot. It is not hot enough for fusion, but it's very extremely hot. At these sorts of temperatures, the composition of the sun will become completely ionized. So you have a fully ionized plasma. Okay, quick review, students. What is the composition of the sun? What is the chemical composition of the sun by percentages?
Hydrogen and helium, 98%, 2% metals.
Bang, Austin for the win. Nicely done. So Austin, if I were to ionize both of those gases, forget about the metals for a second. Let's just talk hydrogen and helium. What would I have if I fully ionized those particles? I just want to make sure
A
that
lot of ionization.
well,
Plasma.
that's big. It's a plasma, but what kind of particles are in my plasma soup? What kind of particles would I find in the plasma?
Ionized?
This is what I was worried about. I was worried that we might not be able to have a conversation with each other. We're talking to each other like this right now. Yes, the gas is ionized, but what particles make up the plasma?
Wouldn't that'd be the hydrogen and the helium, right?
Right. So let's start here. What's the composition of a hydrogen atom?
1 proton, 1 neutron, 1 electron.
Well, that's deuterium, but your typical hydrogen is just 1 proton and 1 electron, right?
Okay.
So if I ionize that, Austin, what am I left with?
One or the other.
Okay, so this is the difference between physics and chemistry. In chemistry, when you ionize,
Oh, a charged particle.
but they're both still there. Just because you rip the electron off of the proton, it doesn't mean the electron disappears from the space-time continuum. Let's draw what your plasma looks like. We need a cartoon here. First, I have a lot of protons because protons are the nucleus of a hydrogen atom. And then, Austin, those electrons did not get thrown away. The electrons are also sitting around. They're floating nearby, but their kinetic energies are too high to be bound to the protons. So they're all kind of moving in different random directions, right? There's also the occasional alpha particle. What the hell is an alpha particle, students? Tell me you love particle radiation. What is an alpha particle? No? No one can tell me what an alpha particle is? I thought y'all were cool. Guess I was wrong, huh? Dang. No one? The 3 types of radiation discovered by Madame Curie? Alpha, beta,
Helium
gamma?
nucleus.
Oh, who said that?
Kevin.
Kevin. Kevin knows it's a helium nucleus. Kevin, don't you go away on me, son. What's the composition of a helium nucleus?
So you have 2 protons,
Uh-huh.
2 electrons.
Electrons are.
Oh,
Want to try
nucleus.
again?
It's the 2 protons and the 2 nucleus.
Neutrons.
Neutrons, sorry.
Let's draw an alpha particle together, okay? 2 protons and 2 neutrons stuck together. Nature loves alpha particles. Nature loves these things. This is what your plasma looks like. Now, the radiation zone is called the radiation zone because why? I bet you guys could guess why we're going to call it the radiation zone. How is energy transported?
Radiation.
Exactly. And you might ask me, why does energy transport switch over from convection to radiation? The reason why has to do with ionization. When the gases are neutral, photons can be absorbed by neutral gases, and that heats up the gas like a hot air balloon. But photons do not get absorbed by plasma particles. Photons get scattered by plasma particles. The types of photons you'd have in a bath of 10 million Kelvin are probably X-rays and gamma rays. Suppose I'm a little short wavelength high energy gamma ray. I am going to travel through the plasma soup, and I am going to bounce and ricochet off the plasma particles. Bing, 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 bing. Each time the photons bounce into plasma particles, they shift their energy and they lose a little bit of energy that they translate to the gas. Weirdly, you'd think that the photons would be most likely to hit a helium nucleus or even a proton, but it turns out that the quantum mechanical cross-section of an electron is much greater for a photon. Photons bump into the electrons more frequently than the protons. Why do you care about this? Why is this interesting? because it takes a long time for all of those photons to bounce and ricochet their way through the sun. The process by which photons bounce off of these particles is known as a random walk. It's a statistical idea, and I've got a cool story about it that I totally don't have time to tell you. But let me tell you this. The average time, the time for one photon to travel through the radiation zone is approximately 1 million years. Put a big giant exclamation point next to that. Okay, Chris, what this means, my friends, is that if nuclear fusion stopped in the sun tomorrow, the sun would continue to shine for another 1 million years as all of those photons were to leak their way out. That's kind of amazing if you think about it, right? Okay, I got time for one more tidbit, and it's the, Arunsak is, oh, okay. Is that what you were looking for? The angle? Yeah, okay. I got time for one more module, and that's the nuclear core of the sun. I wanted to spend even more time on it, but we'll get a little bit in. Okay, let's, Arunsak, can I erase? All right. Now we get to our most favorite part, and I may ask you one or two little test questions on this part, so please take some notes here. At last, we get to the nuclear core of the sun, okay? Here, energy is not being transported, but energy is being generated by a type of nuclear reaction called nuclear fusion. Class, who knows the difference between fission and fusion? Maybe I should ask a more basic question. What is a nuclear reaction? Do you know what I mean by a nuclear reaction? Oh, shit. Does anyone?
I think fusion is when like the protons and the neutrons are kind of mashed together.
Yeah, let me show you a slide that I think will help here, okay? Nuclear reactions involve the nucleus of an atom. A nuclear reaction means you are altering the nucleus of one of your atoms. That makes it different than chemistry. These two pictures will show you the difference between fusion and fission. In fission, you take a big fat nucleus like uranium-235 and you whack it with a high-speed neutron, and it splits apart into radioactive daughter nuclei like radioactive cesium and rubidium, and it releases a gob of energy, usually in the form of gamma rays. So fission, as someone said in the chat log, is splitting apart. Fusion, however, is when you glue small nuclei together. So in fusion, you take little tiny nuclei like protons, and you keep sticking them together until you make a bigger nucleus like a helium nucleus. This also releases energy, just a little bit less. The sun uses nuclear fusion, but our nuclear power plants and most of our atomic weapons use nuclear fission. Fission is a dirty, nasty form of radioactivity because after you split apart a big fat nucleus, you have leftover radioactive byproducts, which irradiate the ground, and they can mutate you and turn you into a teenage mutant ninja turtle. Obviously, it would be so much cooler if we could do nuclear reactions the way the sun does, because it's a clean and very sustainable form of energy generation. I may have more to say about that, plus a dangerous demo in just a moment. But let's make sure, yeah, in a fusion reaction, they come together, they're fusing. Now, in the core of the sun, the temperature reaches a key value of 15 million Kelvin. And 15 million Kelvin is a number that I want you guys to try to remember. It's the temperature for hydrogen fusion. In the sun, hydrogen fusion is going to proceed by a reaction known as the proton-proton chain. And this is going to be your first crash course into nuclear physics. Normally, you don't get to study nuclear physics until you've been in Physics Academy for like 4 or 5 years. But what's cool about astronomy is we get to do a little bit of all of it. So you should enjoy this because normally this isn't something you'd be able to study right away. The reaction is called the proton-proton chain, which is sometimes unimaginatively abbreviated as the PP chain. I kid you not. Okay, and the PP chain, the proton-proton chain, is a reaction in which 4 protons are going to come together to make 1 helium nucleus and release energy in the form of a gamma ray or 2 gamma rays. So let's start by writing down the net reaction. The net reaction could be written in the following way. 4 hydrogens. Hey class, what is the nucleus of a hydrogen atom? I got to make sure we drill this in, otherwise you're going to get lost here. What's the nucleus of a hydrogen atom?
2 neutrons, 2 protons. 1 neutron, 1 proton.
Myself. Okay, so that's a helium nucleus, okay? A helium nucleus is 2 protons and 2 neutrons. No. Okay, guys, it's time for us to get something straight. There are no electrons in the nucleus of an atom, okay? The nucleus of an atom contains nucleons. What is a nucleon?
It's the neutral particle.
That's a neutron. A neutron is a nucleon, but nucleons are not neutrons. Thank you, Gianna. It's a proton or a neutron. Hey, Gianna, since you're telling me intelligent things, Gianna, do you know what the nucleus of a hydrogen atom is? Oh, damn it. I'm going to face palm here. Okay. Yes, Daniel, 1 proton. That's it. Okay. 4 hydrogens, 4 protons are going to slam together to make 1 helium plus 2 gamma rays. Okay, you know what? Guys, it's not your fault. You're still learning, but we're going to have to draw this out like pretty pictures, okay? We're going to draw this out like pretty pictures. But I want you to write this down. I'm going to need to erase this whole board, and I'm going to need to write this in terms of a pretty picture. So get that down. I'm erasing this. The board's getting really nasty. Okay. Let's do a note module on the 3 steps of the proton-proton chain. Let me angle this. Okay. The 3 steps of the proton-proton chain. Because many of you keep forgetting what the nucleus of a hydrogen versus a helium atom is, we're going to write it out first in chemical notation, and then we're going to draw the picture underneath to make sure that you lock the 2 images together, okay? So here's step 1. Step 1's kind of a doozy. So if we were to write it in chemical notation, we would write a hydrogen fuses to another hydrogen it creates a particle called a deuteron. This is going to sound like total Greek to you guys for just a minute here. It's going to create a deuteron, a positron, and a neutrino. Okay, I'm going to explain each of these labels, and then we're going to draw a picture, okay? So a hydrogen nucleus is just a single proton. So let's draw a proton underneath the two hydrogen symbols. They are going to fuse together to make the nucleus of a deuterium atom. Do you guys remember what deuterium is? What is deuterium? Deuterium is an isotope of hydrogen. It's one proton and one neutron. That means one of our protons is going to transform itself into a neutron. I bet you didn't know that was possible. You can transmute a proton into a neutron. You want to know how you do that, Arunsak? With antimatter, okay? Introducing what's called a positron. A positron is a microscopic little particle with the same mass and size as an electron, but it has a positive charge instead. So draw a little tiny positive charge. This is called a deuteron, and this is called a positron. And this little particle here is a microscopic massless particle known as a neutrino. A positron is an example of antimatter. Remember, students, that when I first introduced atoms to you roughly 1 week ago, I told you that a proton is a big fat positive particle, a neutron is a big fat neutral particle, but that an electron is a little microscopic negative particle. And I told you that the electron is tinier and much lighter than the proton, but somehow their charges were equal and balanced. In 1931, a physicist named Paul Dirac sat about meditating on how weird nature is and how screwed up it was that nature would have a big fat positive particle and a little microscopic negative particle balance each other out. And Paul Dirac wondered and hypothesized if nature might be capable of reversing the process. He wondered, could it be possible for nature to create a big fat negative particle, just like a proton, but with a minus charge? And could nature make a little microscopic electron, but instead give it a positive charge? He referred to these particles as antimatter. He presented the paper to a conference of physicists at the American Institute of Physics, and they all laughed at him and said, dude, what the fuck are you talking about? This is physics, bro. You can't just make shit up. You can't just dream about antimatter particles and then present this paper to us as if this was real science. This is you being stupid and being high, okay? And they laughed him out of the conference. And guess what? 30 years later, they found all this stuff in particle smashers. They started smashing protons together, and sure enough, even though he had made it up, even though he had just dreamed it out of his mind, it turned out to be real. And we observe antimatter particles in giant collisions that take place. How many of you know about the LAG? It does not have a higher energy density, Kevin. It has the same energy density. How many of you guys know about the Large Hadron Collider? Have you heard about that before? Yeah. So what's up with that? The Large Hadron Collider is the world's basically it's world's most powerful atom smasher. And I just want to show you guys, in case you've never seen this, this is what a picture of the Large Hadron Collider works like. And this is kind of a pitch for you guys to think about going into science. Why punch into your shitty office cube with fluorescent tube lights and drop ceilings when you could go to work in the bloody Death Star, okay? This is what the office looks like if you are a particle physicist. And what the Large Hadron Collider is, it's a 27-kilometer long ring of magnetic tubing that spans the border between Switzerland and France, okay? So it's a gigantic ring, 27 kilometers long. Here's a picture of it. And what they do is they use magnetic tubes to ionize plasma until you get just protons, and they whip protons around the tunnel at the speed of light, and they smash the two protons together. And when they smash these protons together, do you want to know what happens? Explosions, little nuclear explosions that create all kinds of bizarre particles, sometimes including antimatter. I'd like to say more on this, but I'm going to run out of time, and I want to at least do the 3 steps of the proton-proton chain. So you can think of the purpose of the positron is the positron removes the positive charge from a proton, turning it into a neutron. The neutrinos are weird. Maybe I'll talk about them later. A neutrino is a microscopic massless particle that comes from nuclear reactions, and neutrinos are so tiny and microscopic that they can travel throughout the entire sun as if the sun was transparent glass. They say that to have a 100% chance of getting a neutrino to bump into one single atom, you'd have to pass a neutrino through a slab of lead that was 1 light year thick. So neutrinos are like these microscopic subnuclear particles. They're real weird. I'll tell you about them later. Okay, the other 2 steps are not complicated. In step 2 of the proton-proton chain, your newly formed deuterium nucleus, your deuteron, is going to smash into another proton, a hydrogen nucleus. It's going to form an isotope called helium-3, and it's going to emit a single gamma ray. Let's draw that out as a picture. Deuterium is 1 proton and 1 neutron. It's going to collide with a hydrogen atom, which is 1 proton. And when they smush together, they are going to make an isotope of helium called helium-3. This is an unstable nucleus. It does not have enough neutrons to be happy. And the gamma ray is actually a tiny little wiggle of electromagnetic radiation. Remember, students, that a gamma ray... Did anyone else lose audio? Can you hear me, Christopher? Okay. I'm almost done, guys. I know it's time for break. Just let me finish this. This is where all of the sunlight that comes from the sun is generated. You know, if you sit on the beach down in Narragansett Bay and you're drinking a pina colada and there are sunbeams tickling your face, every single beam of light that hits your face began its life in step 2 of the proton-proton chain. That gamma ray is where all of the energy of the sun comes from. Finally, in step 3, step 1 and step 2 have to happen 2 times to create 2 helium-3 particles. So helium-3 collides with another helium-3 nucleus. They mush together to create a proper helium-4 nucleus. And they leave behind 2 protons as extra byproducts of the reaction. Remember that the nucleus of a helium atom, shoot, I'm kind of running out of space here, is 2 protons and 2 neutrons. That's the only particle I'm going to draw here. So 2 protons and 2 neutrons. Every time one of these reactions takes place, you transform the chemical composition of the universe itself. The universe ends up with a little less hydrogen. The universe ends up with a little more helium. And some of the tiny mass that was associated with the protons actually gets converted into light by Einstein's famous formula, energy equals mass times the speed of light squared. That's what's happening during the process of fusion. You're taking mass and you're taking a tiny bit of that mass and converting it into energy in the form of gamma rays. We are going to be studying many more nuclear reaction sequences after the midterm exam. You're going to learn about all the different types of stars. Stars are basically little fusion machines. They alter the chemistry of the universe. They create the atoms that make up the cells in your body, the core of our planet, and they're also cool to look at. Okay, at this point, you guys clearly need a break, all right? Let's take 15 minutes, and let's talk about what we're going to do after that. I'm going to go over the format of the exam. I'm going to tell you which chapters it's going to cover. I'll tell you the number of questions and what the exam is going to look like. I'll talk about strategies of how we're going to do the exam together, and then we're going to do some practice problems. Does that sound good? Let's take a full 15 minutes. I think you're going to need it. Okay, Astronomy 1020, welcome back to our session where we're going to do some midterm exam preparation. I'm going to go over the format of the exam and some other key things that you'll want to know. But I would like to take this moment to remind the class, both day students and night students, that I have given you guys an amnesty, a general amnesty for homeworks and labs this week. So if you missed Tuesday's lecture, this week I'm letting you turn in any missing homework or lab that you might have screwed up on. That way you can study for the test and plug up those zeros that you might have gotten. Remember, students, that if you're turning in all of your homeworks and all of your labs, as long as you take the exam and get something on the exam, you will not fail my course, okay? The only way you can fail this course, I will check, Gianna. Just get it in, okay? I will check. The only way you can fail the course is if you have zeros for homeworks and labs. Or I suppose if you flake on the exam, if you have a 0 on the exam, then you could also potentially fail the course. But as long as you have all of your homeworks and labs in, you can't screw this up, okay? Now, obviously, Blair, it's much more important to review the homeworks than the labs, but I will say that some of the stuff that we did in lab is going to be on the test. So I'm going to say both. Like, you know, one of the labs that we did with the period of the satellite? That's going to be on there. One of the labs is on ellipses. That's going to be on there. Obviously, scientific notation is going to be on the test. Let's talk about it. Okay. So first of all, the midterm exam is going to be a whopping 100 questions, and the entire thing is multiple choice. But before Austin starts jumping up and jubilating to the heavens, remember that a multiple choice exam can be tricky, especially when there are 5 possible answers each time. Let's analyze this for a second. If you are filling out random bubbles, you have a 1 in 5 chance of randomly guessing the correct answer. If you answer with a 1 in 5 probability, that corresponds to a 20%. So you should be able to at least get a 20 out of 100 on the exam if you are at random, okay, just by button mashing, just by mashing the buttons, you should be able to get 20 out of 100 points, even if you know absolutely no astronomy, okay? Obviously, we call this being at random. And I'm hoping that you guys know enough astronomy that you'll be above the random floor, okay? All right, there are 3 parts to the exam. The first part of the exam, which is roughly 30 points or 30 questions, is the diagrams section. In the diagrams section, I'm going to show you one of the illustrations or pictures that we've looked at during the course of our lecture. And several of the questions will be on those different parts, okay? So in your diagrams section, this might be number 1, and this thing might be number 2, and that might be number 3. And then I'll ask you, what is the appropriate vocabulary word or term for this thing in the diagram? What do we call this thing in the diagram? What do we call this thing in the diagram? So this is about studying the pictures and the diagrams, but it's also about knowing your vocabulary terms, okay? For your diagrams section, there'll be probably either 5 questions by 6 pictures, or there might be 5 pictures each with 6 questions. Actually, I think that's how it's going to be done. I think it's 5 pics multiplied by 6 questions for each picture. Obviously, things with layers are a good thing to study. Things with zones, coordinates, things like that. Those are the kind of things you can expect to be on that section. The diagram section is usually one of the easier parts. The second section, which is also 30 points, is what I like to call general multiple choice questions. And the general astronomy questions are usually non-mathematical, although some of them are mathematical, but they involve small bits of math. So this is either non-math or it might be small math. In other words, the types of questions that you can expect in this section are, I'm going to ask you things like, what is Newton's second law of motion? What is Kepler's first law of planetary motion? I might also ask you, suppose the moon was twice as far from Earth. Would you still expect to have a total solar eclipse? These questions can be technical without requiring math. Suppose I asked you this question, students. Which of the following photons has the greatest energy? And I said, visible light green, visible light purple, a radio wave, an ultraviolet photon, or an infrared photon. Which of those has the greatest energy? Would you know the answer? Well,
Infrared?
we've got some studying to do, okay? But the idea is that question you could answer by knowing something technical and yet not having to do a calculation. Let me tell you how you should have done that question. You should have done that question by arguing that the energy of a photon is inversely proportional to its wavelength. So the shortest wavelength photon will have the highest energy. Which of the photons that I mentioned had the shortest wavelength? Not infrared, Arunsak. That's right, Kevin, ultraviolet. Kevin, that's an example of how knowing a formula can influence your answer, but you didn't actually have to do a calculation. Do you guys see what I mean? All right. Now, at last, we get to the most important part of the exam, which is the mathematical applications. That's going to be 40 points worth of exam, roughly. Now, the math applications are going to be in many ways almost identical. Well, not identical, but they're going to be similar in spirit to the homework problems. What I will do is for a set of questions, you'll have a box with a bunch of givens. I might tell you the sidereal period of Mars, or maybe I'll tell you the period of one of the moons of Jupiter. And then the following questions, 61, 62, 63, 64, and 65, all the following questions will all be about those givens. Usually the way it will work, let's think about how one of our homework problems would work. I'd give you a problem, and you know how oftentimes you have to do like unit conversions before you plug into the formula? It's going to have that feeling to it. So you guys will first, 61 and 62 might just be convert years to seconds, convert astronomical units to meters. And then in the next problems, you're going to have to use a formula and calculate an answer. By the way, I will warn you guys, sometimes the answers to these questions will depend upon you getting these. Exactly, Blair. If you fuck up the first two questions, you're going to get them all wrong. And do you want to know why I think that's okay, Blair? Because the first two questions are usually dimensional analysis. And if you don't know dimensional analysis, you're not my friend, okay? I don't like you. I don't think that you deserve to exist, okay? Everyone, you need dimensional analysis. And dimensional analysis can help you pick off so many of these questions. So you better be good at that. We'll be practicing that today. Okay. Let's go ahead and let's talk about the chapters that are going to be covered. Basically, everything that's been in our lectures so far will be on the test. Okay. So the chapters that I'm going to be covering, chapter 1 isn't really that important. Chapter 2, all of chapter 2 will be on the test. That involves like the local sky. It involves the small angle formula. Chapter 3, you don't need all of chapter 3. You just need the stuff on Kepler's laws and the stuff on ellipses. If you actually, I bet all of 0% of you have actually ever read the book before. I bet 0 people in this class even opened the book once, right? Or if you have, then
It's still in the plastic.
It's still in the plastic. That's what I expected. I mean, there's a couple of different reasons for that. One is I'm such an incredibly good teacher. You don't even need the book. The real reason, though, is it's hard to carve out time to read in modern life. It takes a lot of time. What I think you guys should do is you should look through the notes and you should redo the homeworks. And if you missed any lectures, you should go back and watch those. Yeah, what is this book that we speak of? Okay, but that's okay. If you didn't buy a book, that's fine, because you can get what you need from the lectures. But I want to tell, just in case someone decides to ever read the book, chapter S1 is, all we need is the equatorial coordinates. Chapter 4 is on Newton's laws and gravity. Chapter 5 is on light and atoms. Chapter 6 we did not cover, but there are 2 mathematical insights or 2 formulas that we need. One is the small angle formula, part 2, and the other is the diffraction limit. Those 2 formulas will most definitely be on the test. And lastly, the chapter that we've done these weeks, chapter 14 on the sun. Up into and including the 3 steps of the proton-proton chain. Okay, before we do some sample problems, I want to talk about a strategy. Okay, listen. When I have a class in person, I treat the exam as a full contact sport. And I like to be there and kind of patrol around the room so that if you have questions, you can ask me. But I'm not above giving a student a little passive aggressive hint if you get really clogged up. Like, let's say you've got one of those problems where you have 5 questions and you're just totally freaking out and you can't think straight. I might come over to your desk and I might say, looks like you need a formula that begins with P. How many formulas are there on your formula sheet that begin with P? Maybe we should look for one. You know, I'll say something snarky like that to you. That's harder to do when we're doing the test online. But here's the proposal I'll make with you guys. I think when we take the test, we're doing it through the multiple choice program on Blackboard. But I think we should all log in together on Zoom, just like any other class day. If you guys want, we can mute and we can hide our videos. We can all be trolls, including me. And I'll putter around my apartment, cleaning dust bunnies and making sandwiches and playing my synthesizer, doing whatever I do. Maybe I'll even grade papers, who knows? But I want to be there so that if you guys have a question, you can unmute yourself and you can kind of ask your question in front of the whole class. And maybe the others will benefit from listening to the answer to that as well. Doesn't that sound like a good idea? I'm not going to stay. I'll probably stay on from like 11:30 to like 2. I won't know if I'll give you a direct answer, but I'm not above giving you a hint. Okay. Okay. Are you guys ready to try some sample problems? All right. Let's do it. So Reardon asks, will the exam be timed? I will be timed in that I will be there from 11:30 to maybe 2-ish, almost 2. After that, you're on your own. I'm trying not to put a time limit on the exam so that if something happens, like your dog chases after the turkeys, what if Blair's turkeys get loose in the middle of her exam? I'd like her to be able to pause and come back to her exam. But I need to have my grades done by Wednesday. So you need to finish up by the nighttime. Yes, Blair, that's a good point. Some of you have really sucky internet, so that's also helpful. But can we agree that by Tuesday night we'll wrap this thing up? That's reasonable, right? Okay. I don't think anyone wants to be working on it later than that. All right, let's start off with a simple basic problem and let me talk about the concept.
Professor,
Oh, yep.
I have a question for you.
Yep.
What will the curve be for the exam?
There is a curve, but it's not for the exam. It's for the mixture of exam, homework, and lab. And Austin, can we talk about that after the exam so that you can understand? It'll be TMI right now. I have a curve for the entire course, but is it okay if I tell you after we've taken the exam?
Sure, that seems a little sus, but sure.
I guess I can understand how you think about it, but the problem is I'm going to have to get into a digression about how I compute your scores. I take together your percentage for your homework, your lab, your midterm, and your final, and I average them with an equal weighting. No, it doesn't depend on the class's scores. And then you have a percentage. I can start off by telling you this, Austin, that a 65% is sort of like a B- in my class. And then it sort of goes in 5-point increments from there. So it's not as simple, but keep in mind, I don't apply that scale until after I've averaged the raw scores of homework, lab, midterm, final. So it is too much. It's not sus, brah. It's just a little too much detail to get into right now, okay? All right, let's try a sample problem. Unlike a typical homework problem, in a typical homework problem, as soon as we set it up, I instantly start to solve it for you. I do not want to do that in this case. I'm going to put the thing up and I'm going to give you guys 5 minutes to work in your own personal hell. You can ask me questions and ask me for hints. You can talk to each other via chat or in person. But the important part is that you try to do this on your own so you can see how scary it will be, okay? So here's a good sample problem. Let's do a problem on something called the ionization potential of the hydrogen atom. Okay. In space, a cold hydrogen atom will feature a single electron in the ground state. It's possible for a single photon of precisely the correct amount of energy to ionize the hydrogen atom in the following way. The photon will come in, and provided the photon has exactly the right energy, the photon will kick the electron right off of the atom. We know that the ionization potential of the hydrogen atom is 13.6 electron volts. Therefore, if I have an incoming photon of 13.6 electron volts, it will have just the right energy to knock the electron off of the atom. Here is your job. Problem 1. Convert the energy. So here's the energy of the photon, okay? Convert the energy to units of joules. Question 2. Find the frequency of the photon. 3. Find the wavelength of the photon. And 4, in what regime of the electromagnetic spectrum is this photon, which can ionize the hydrogen atom? Okay, there's your problem. Take out your pencils, your calculators, and go to town. See how many of these you can get done in 5 to 10 minutes. Use the formula sheet. Oh, you know what? I'm gonna, for the benefit of night students, I'm gonna pause the recording during the time while you guys are working. That way I don't create video bloat with all this dead air. Okay, it's time to check up. The formula sheet is blank. What the hell, guys? Why am I just finding out about this now, Cameron? Everyone, no matter how many times I send the formula sheet, there's always some problems with it. Cameron, are you telling me your formula sheet is blank? That doesn't make any sense. Devin could read it. Did you get it from the email or did you get it from the chat, Cameron? Devin's was fine by email. Oh, okay, I see. All right. Class, can we talk about it? By the way, before we go through the numbers here, I just want to see a show of hands for human beings who share video with me. How many of you humans feel like you got all 4 answers? Show me your hand. Raise your hand if you got an answer for all questions. Shit.
I got up to 3, but I couldn't finish.
Is it
I
Christopher?
only got 1.
You only got 1? Stacy?
Was there a prerequisite for this course?
No. The prerequisite is having a good attitude about life and knowing how to push buttons on a calculator.
I don't have the first one.
Okay, look. I know what you guys are going through. That's why I'm doing this. Of course, it's way harder when you have to do this on your own, right? But you can learn to do it. We're going to be strong. Let me just talk to each one of you. Arunsak got 3 problems. Stacy, you didn't get too far. Kaitlyn, what happened with you?
My calculator, I thought it was broken, but I fixed it and it took me a few minutes. So
It's just it was just too dark in that place, probably. It wasn't broken.
No,
It was probably just dark. If it doesn't get light, the battery runs out. So just keep it near the lamp that's on your right, to the left of you. Alejandra?
I only got 1, the first one, and then I was looking for something about frequency and didn't figure it out.
Emily?
Yeah, that's what kept me up too.
All right.
I only got the first one.
All right, so let's talk about it. It sounds like a bunch of you got the first one. By the way, you better get the first one because it's just dimensional analysis. Why don't you, Stacy, why don't you walk me how, okay, wait, no, Stacy, too much pressure.
I'll do it.
Okay, how'd you do the first one, Austin?
Well, I didn't.
Oh, Ty, that's cool. Ty got the first one. Alejandra, you got the first one, right? So talk to me, buddy. How did you do the first one?
Sorry, I'm eating crackers.
That's okay.
So I did 13.6 EV
Correct.
times and bar. And I put joules over EV.
Nice. To cancel EV, right?
Yep. 1.6 times 10 to the negative 19.
Uh-huh. On top.
Yep.
Right.
1 on the bottom.
Nice.
And I don't know if I got the right calculation because maybe I don't know how to use this thing. It's I got maybe this number's too long. 2.7176.
Okay, we got to get something straight first of all. This part of the number is not the number. That's the number. Your power is more interesting to me. Give me 2 significant figures and then your power of 10. Do you even understand what I mean by that, Alejandra?
No.
Okay, someone just said it.
Oh,
I got-
I want to hear 2.2. I want to hear what Blair said. Blair said it the right way. Like, fuck the 2.1967345. That doesn't matter. What matters is the first 2 digits and the power of 10. So the way Blair said it was 2.2 times 10 to the minus 18. But Blair's answer is still not good enough, Blair, because you didn't put any fucking units, and the units matter.
Why is it to the negative 18 if I got to the negative 17?
Because you screwed it up. And it's time for us to figure out what
Okay,
happened.
how do I stop doing that?
I will show you how. First of all, what are the units? Because I can't even cope unless I get units on that number. Joules, that's right. Okay. Okay. Do you want to know how I know it's going to be negative 18, Alejandra? I can see that this is 10 to the minus 19. And I know that if you multiply 13 by 2, you're going to get like 26 or 22. And that 22 will kick this back 1 to negative 18. Here's what I suspect you did. I can't know exactly what you did, Alejandra, but I bet I know what you did. I bet you made the classic rookie mistake of trying to type this in as times 10 to some power. Is that what you did? And you're going to get it wrong every single time if you keep doing that. Let me tell you about something we talked about on day one, Alejandra, the EXP key. That's the only key you should be using for scientific notation. Do you know what I'm talking about?
I use the EXP key.
Well, can I show you how I would type it, and then you can tell me what you did differently? I would type it as 13.6 times 1.6 EXP negative key 19. And then I would hit equals. So what did you do?
I think I put 10 EXP.
All right, there's no 10 EXP. It's just EXP. EXP, EXP contains the times 10, okay? So that's what happened. So from now on, you're just going to hit EXP, right?
Yep.
And by the way, Alejandra, I'm talking to you, but I'm also talking to all the rest of these cats too. If you made that mistake, I bet there's 5 more people hiding in the troll quarters who made that same mistake. All right. So this is a good thing to talk about. So I guess all of you, that's as far as you got, except for Arunsak, huh? Arunsak, why don't you show these cats how it's done? What did you do for number 2?
So we're asked to find frequency.
And we were given what?
We have energy.
So what he's doing is he's going to find the formula sheet. Let me share screen with you guys for a second here. So let me tell you what Arunsak did and what I expected you guys to do. He then goes to his formula sheet and he says, I have an energy and I need a frequency. Kaitlyn, what is the energy going to start with? With letter
E.
And what's the frequency going to start with?
F.
So you need a formula that has E and F. Arunsak found it. Did any of you find it? Christopher, you couldn't find it? Arunsak, tell him what you found.
E equals H times F. And then
This formula has energy and frequency right there. Do you see that? That's what I needed you to do. Now listen, Stacy asked me about prerequisites. Stacy, obviously this course involves a little bit of baby algebra. If you can find the formula, if you have trouble rearranging the formula, if your algebra skills are sucky, I will help you during the test. You could literally say to me, hey, B, I've got the formula, I think, but I need to solve it for F, and I'm not sure if I did that right. And then I will show you how to rearrange the equation. I don't want you to get tripped up on algebra. I want you to get tripped up on concepts, okay? Okay, so Arunsak, why don't you show them what you did next? So let me write down the formula, okay? Arunsak, did you rearrange this?
Yeah, so you get it to solve for F, which is F equals E over H.
Yeah, you're going to take the H and put it down there. So F equals E over H. But remember, students, I would be willing to help you with that if you have trouble rearranging it. Okay, what did you do next, Arunsak?
So I plugged in the energy, which is the 2.2 times 10 to the negative 18 joules. And then the H is the constant, which is on the paper.
Yeah, let me show the students where that is, Arunsak, because they might not have found it. Arunsak then recognizes that H is given here, along with its units of 7 times 10 to the minus 34 joule seconds. Okay, guys, punch them up.
But first, I got a question.
Yeah.
So at the very first question, I got 2.18 and I didn't round that to 2.2.
Doesn't fucking
Will I
matter.
get the,
It
Okay.
doesn't matter. It's not going to change your answer one little bit. Devin, I like your number. I don't like your units. Actually, I don't even like your number. I like neither your number nor your units. Try it again, Devin. Plug it again. Arunsak, what did you get? Devin, do you know how I knew that your number was wrong? I knew your number was wrong because when I look at numbers, I pay attention to the power. I know that -18 plus 34 is going to need to be a power of +10. So when I saw you say 10 to the negative something, I immediately went, eh. Right, okay. Okay, Emily, I like what you got, but can you read it to me like a normal person?
Oh shit. Hold on, I accidentally just deleted it.
It was 3.14 times 10 to the 15.
Okay, 3.14.
Ah, Gianna. Gianna's my girl. Look at that. 3.1 times 10 to the 15, 1/seconds. Gianna, you rule. That's what I like right there. I like that. A number rounded to 2 sig figs plus units. That's how you keep it classy, Gianna. That's how you keep it classy. Okay, what are we going to do next? The next question is to find the wavelength, right? Arunsak, you said you got to the next question. Which formula did you choose?
So we now have, I chose C equals wavelength times frequency. And
Okay,
then you rearrange.
that. So for number 3, which is find the wavelength, he used the formula speed of light is wavelength times frequency. And then Arunsak, you would have had to solve that for wavelength, correct? Stacy, do you know how to solve that for wavelength? Tell me what the formula is, Stacy.
Okay. See, okay. So it would be 3 times, wait.
No. Can you give it to me symbolically first? I just want to know if you can rearrange this formula to solve for wavelength.
Oh, okay. By wavelengths, it would be wavelength equals F over C. Or is it C over it?
Yeah, because look.
Okay. Yep.
At the top, you have to push frequency to the other side, right? Okay.
Yep.
So but that's something you can ask me during the test. If you're a little unsure about it, you can say, hey, B, did I rearrange this right? And I will tell you, and I will tell everyone else. So C divided by F. Okay. Now we plug in our values. You get the speed of light right from the formula sheet. It's 3 times 10 to the 8 meters per second. And the frequency was 3.1 times 10 to the 15 hertz, or cycles per second. Devin, you could totally use that formula. There are 2 different ways to solve this problem. I decided to teach you guys whatever way you naturally chose. But Devin's question, which the class should understand, is yes, Devin, you could rearrange this one as well. It's simply a matter of taste. Okay, what did you get? Talk to me, people. Time is money here. I ain't got time for you to be slow.
9.7 times 10 to the -8th
meters.
Thank you. Notice, Emily, I liked how Christopher saved you by including units. I was about to kind of pop off there for a second. Okay, now Arunsak said he had trouble getting to question 4. I don't know if you had trouble getting there or if you had trouble thinking about it. Question 4 asks, in what regime is this photon? Arunsak, did you not have enough time, or did you not know what to do? What was the situation there?
I knew what to do. I didn't have enough time, but I finished it out while you were explaining stuff.
Okay, so tell us how it works.
So we want it in nanometers first and foremost.
Okay, wait, not everyone's going to follow that, Arunsak. I was actually wondering if you were going to pick up on that. Do you hear what he just said? We should convert this to nanometers. Arunsak, why should we convert it to nanometers?
Because that's how we measure wavelengths in nanometers.
A better way to say what you just said is, Brendan, when you taught us the regimes of the electromagnetic spectrum, you did so with this slide here, number 63. And this slide lists most of the wavelengths in nanometers. So because I taught you the EM spectrum in nanometers, you aren't going to be able to peg where 9.7 times 10 to the minus 8 meters is. You've got to convert to nanometers. Did everyone hear that? You got to remember to do that. Okay. So help us convert it, Arunsak. Actually, no.
There was a conversion rate.
No, stop for a second. Sorry, Arunsak. Stacy, you had trouble even with the first one. I need you to do some dimension.
No, actually, I got the first one right. I just lacked confidence, but I'd really rather just hang back and listen and learn, if you don't mind.
That's okay, but can I tell you something? Something that I know from being in the professor chair? Yes, it's more comfortable to sit back and listen and not participate. But by forcing yourself to participate, even if it's a little embarrassing sometimes, you learn more that way.
All right, bring it. I have no pride, no shame. I got it.
All right, okay, that's what I want to hear. That's
all right, I got this.
So
I'm a little lost though. I won't laugh.
Okay.
I mean,
that's okay.
It came back easily, but
it's okay to be lost. Why don't you work with me and
thank you, Arunsak.
All right,
take your mic off and chime in.
Stacy, you and I, but mostly you, are going to convert this to nanometers. So tell me how to do it.
All right, nanometers. So it's we're going to convert it. So are we going to do dimensional?
Hell yeah, we are.
Of course we are. Okay, so you're going to put let's see, 9.7 times 10 to the 8th.
Negative 8.
And then we're going to do times.
Remember, Stacy, the first part of dimensional analysis is write down the number to convert with its units.
Meters. Yes.
That's right. Okay.
Excuse me.
Now what's
all right? You're going to put your multiplication and your bar.
Yep.
And you're going to put your meters on the bottom because it always goes on the bottom.
Right.
And then on the top, I'm sorry, we're converting to nanometers. So that conversion would be 1 times 10 to the 9th meter.
Wait, is it positive or negative? Okay. That's the second time you dropped a negative there. So watch out for that.
Did I?
Yeah. Look, are you getting it from the formula sheet?
Oh, I dropped it on my form. Shame on me. Sorry.
Okay. If you look down here, Stacy, can you see my screen right now?
Yes. I actually have it on my wall, which is why I keep looking at my wall.
That's gangsta.
Yes.
I like that.
Yep.
Okay, but make sure the negative is in there, okay?
Negative, yes.
I was actually wondering what you were looking at up there. I didn't know if that was like a second monitor. I was kind of curious.
No, it's on my wall right there.
Oh, nice. The wall of Astro. Hey, look, don't forget, Stacy, it's also on that formula sheet, and it's negative 9.
Yep, okay. Negative 9, yes, sorry.
All right, so tell me what number top and bottom again?
All right, so on the top, on the bottom would be 1. And on the top would be 1 times 10 to the negative 9.
Okay, and now you punch it up, or you can add.
No, I'm punching it up because I want to practice, please.
Oh, wait a minute. No, sorry.
Nope, that's wrong.
This is all fucked up, isn't it? Yeah. Gianna was like, hold your horses there.
Thank you. So actually, you want to flip those.
If you had done positive, ironically, if you had done positive 9, 1 meter is 1 billion nanometers. But I don't think you should mess around like that. I think you should do it exactly the way you see it on the formula sheet. 1 nanometer
times 10. Yes, thank you guys.
Is 1 billionth of a meter. That's how you should do it. Okay. 9 plus 8 gives you 10 to the power of 1.
9.
What's your answer?
I'm writing it down. Okay, I'll do it here. XP negative 8 divided by 1. exp negative 9 equals, I got 97, which cannot be right. Or can it?
What is the right answer?
It is 97 nanometers.
People are always like, this can't be right, as if they knew what the right answer was.
I know. It was too easy. It's never a number like that.
Well, sometimes it is.
Thank you. Thanks.
In what regime of the electromagnetic spectrum, Arunsak? Take us home. And thank you, Stacy, for putting it along there.
Really? I can't do that? You're going to take it from me now? At this point? I'm in this.
Okay, fine. What's the regime? Give me the regime.
No, hold on. I'm looking it up. Let's see. I'm in this deep. I might as well. So where are we? We're 97.
Yep.
Oh.
I like your spirit. I like your spirit.
Well,
you can
I
use this
regret
guy
it
here.
already.
Here's the
90. It'd be ultraviolet?
Yes.
Oh.
Ultraviolet photons ionize hydrogen.
Bam.
Okay. Now listen, guys. You eventually all collectively worked through this, but you're a little slower than I want you to be. Okay. But hopefully that built some confidence. Kaitlyn, are you cool and stuff? You look like you're giving me this. Maybe it was that refreshing beverage you were drinking that's helping you get through this. I can't hear you. You're muted.
You didn't see anything.
Oh, I didn't see anything. I don't know what you're talking about. To be honest, I thought about having a refreshing beverage too, because I knew I was going to need it to get through this here, but I went for seltzer instead. Anyways, what's your issue, Kate? It looked like you were having an issue.
I got 9.7 times 10 to the negative 17. And I don't know why.
I can tell you why. Guess what -8 plus -9 is? -17. That tells me that what you did, Kaitlyn, is you screwed up and you put 1 meter is a billionth of a nanometer. Isn't that what you did?
No.
Well, can you hold up your paper?
I have it on the bottom.
Can you hold up your paper?
Yeah.
Wait, let me go to full screen view on you. Hold on. Can you hold?
Oh, I'm sorry.
Oh, now it's giving us.
Can you even?
Hey, where's your times 10, girl?
Times 10? Did I forget it?
Yeah, but
No, it's in there. Oh, I did forget it there
but
on
hold
the
on.
end.
Can you hold it up again? That's not the issue. That's not really the issue.
Oh, God, okay, I'm sorry.
Hold it up again.
Right.
One sec. I don't. You just punched it in all wacky.
Oh.
Punch it into your calculator again.
All right, so 9.7 EXP -8 times 1 EXP -9 equals, right?
Wait, divided by. It's on the bottom, right?
Divided by. Okay, that's my issue.
So you
then.
you wrote it. You did exactly what I said, but you wrote it correctly. You just. Hold on a sec.
I just typed it into the calculator.
I've got this weird thing going on in my recording where, Kaitlyn, you and I are like sharing the speaker view, and I don't know how I did that. And I want to get out of, as nice as you are to have there in the window, it's just, why am I splitting this with you? What did I do wrong? Does anyone know how to use this better than me?
Try pinning your own video. If you I think you right click and then you pin your own video, you stay there.
So normally what I do, Arunsak, is I double click on my face and I fill up the whole screen, but Kaitlyn is now currently on the screen with me. So you guys are all in little boxes on the side and me and Kaitlyn are like side by side, but I want the recording I want people to be able to see the whiteboard. How did I do that? Remove pin. Oh, okay, there we go. Hold on, let me remove pin on Kaitlyn. There we go. Okay, I figured it out. Sorry, that was weird. Okay, Kaitlyn, you had written it right? But remember, Kaitlyn, and remember anyone else who's going to make this mistake as well, that might say times. Kaitlyn, are you looking at me? This is on the bottom, so you have to divide, right? Okay, she gets it now. Can we move on and try a new problem? All right. Okay. The next problem is on a geosynchronous satellite. Just a moment. We got to move faster, okay? Introducing a geosynchronous satellite. Fudge. The name of the geosynchronous satellite is SATCOM. SATCOM has a mass of 40 kilograms. SATCOM has an orbital height above the surface of Earth of 36,580 kilometers. In this problem, you will need the mass and radius of Earth. The mass of the Earth is 6 times 10 to the 24 kilograms. The radius of Earth is 6,400 kilometers. Students, we need to draw a diagram, and I'm going to help you draw the diagram. Here's Earth. Here's the radius of Earth. Here's the mass of Earth. And then somewhere up high is the SATCOM satellite. Okay? Its mass is 40 kilograms. Okay. 3 questions. 1, find the orbital period of SATCOM in seconds and in hours. 2, find the force of gravity. Between Earth and SATCOM. 3, find the escape velocity from SATCOM's position, from SATCOM's orbit. Okay, go to it, take a few moments. Don't waste any time, guys, because time is our enemy right now. The more problems I get to show you, the better prepared you'll be for the test. I've had that problem before when sharing Excel files. I think if you edit the file, it automatically saves it to Microsoft Office or something. I guess I got lucky because my schedule was already what I wanted. Guys, I don't want anyone spacing out on me. Kaitlyn, do you know what you're doing? Sorry, I can't hear you, buddy. You're muted.
Yes, I'm just looking at the conversion tree.
Okay, I'm sorry. It just looked like you might you might have been lost. I apologize. How about the rest
No.
of you guys? Are you working? Is anyone stumped?
I'm stumped.
Okay, Arunsak, are you stumped on finding the formula? Is that the issue?
I don't know. So like to find the period, I don't know what I'm looking for at all in the sheet.
Well, it's time for a passive aggressive hint. Arunsak, what does period begin with?
P.
And how many formulas do we see with P? Let's look for them. How many formulas can I find that have P in them? Does this formula have P? No. Where's my annotate tool? Does this formula have P? No, no, no,
I see
no.
a P squared.
Where do you see that? Where do you see that
Down.
piece? Hold on a second.
Scroll.
All
P
right.
squared equals P3.
There's a P, but maybe we should check all the formulas with P. What other formulas have P?
Newton's third law.
So we have two formulas that have P.
Oh, okay.
I wonder which one is the right one. I wonder if any intrepid students might know. What the heck is A, says Devin. Indeed, what the heck is A? Hey, students, I need you to answer me this riddle. Which formula that involves P is the right formula?
I think it's Newton's, right? Because Kepler planets.
Kepler's only for planets going around the sun. Exactly, Arunsak. So you need the Newtonian version. Okay, let's tackle Devin's question to give him a push. Devin needs a hint. What the heck is A in this formula? What is A? Actually, someone said it in the chat, I think. Now, let me go back to the chat.
Isn't it the radius plus the height?
Excellent. A is the center to center distance between the two objects. So what Stacy and I apologize, someone else in the chat log also noticed it. Here's the next hint, Devin, a very important hint. A is the radius plus the height. To answer your question more properly, Devin, A is the semi-major axis of orbit, which is kind of like the radius of orbit. Hey, Runsack, what units do you think you need for NK3?
Can I solve this first?
Okay, like shut up and leave me alone, Brendan. Is that what you said? Yes, you can solve it. Exactly, Devin. Exactly. This one's for you, Kaitlyn. I think it's about that time. Now, let's resume this recording. Can we talk about how we solved this first one together? Because I think some of you got there but had trouble plugging it in. Shall we set it up? What is the A? What did you guys get for A? Jesus Christ, hold on. All right, what did you guys get for A? (42,980 kilometers). But remember, was that Blair? Remember Blair? Where are you? Oh, no, that was Kaitlyn. Sorry. Kaitlyn, you have to convert that to meters, don't you? All right, Kaitlyn, sounds like a you job. Would you help me? If you already did it, you can tell me what you got in meters, or you can walk me through it.
Nope, I haven't converted it. So
Okay, well then that's a great opportunity for you and me to hang out again. Okay, so let's do this here. So 42,980 kilometers. What do I do next?
an X bar.
Yep.
Yeah, with kilometers on the bottom,
Yep.
meters on the top,
Yep.
and I'm just gonna look at the conversion sheet 1 second.
Yeah, Devin, don't forget you guys need MKS units. That's why we're doing this. Yeah, the conversion sheet has meters to kilometers. Or you can just remember what a kilo is.
So you're gonna put 1,000 on top and 1 on the bottom.
Okay. And so what's your final answer?
So it would be 42,980 times 1,000.
Yep.
42,980,000.
Or do you want to just round up to 43 million? Because fuck it, right?
Yeah, sure, that's fun.
Okay. So I would just instinctively round it to 43 million. Okay. Now we got to set up our equation. I'm going to put the square root on the other side because that's how we did it in our lab. P is the nice big neat square root of 4 times pi squared times 43 million meters cubed divided by big G, which we can look up on the formula sheet. Big G is always 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Devin pointed out that we can neglect the mass of SATCOM, so we can just put in the mass of the Earth, 6 times 10 to the 24 kilograms. Okay, shall we punch it together? Or let me let you guys catch up while I sip a refreshing beverage. Okay. Well, Gianna, that's why we're practicing, right? Gianna, if you, Gianna, you know, you're talking to me through chat, so it's a little harder to get quick feedback. But if you have any questions about why I did this, please feel free to ask, and I'll explain. I was hoping this would be obvious, but I guess not. Alejandra's having a meltdown. Are you okay? Okay. Talk to me, buddy. Alejandra, what's going on?
I'm so confused. I don't know how to do any of this.
Okay, well, that's why we're practicing together, right? If you're confused, that's okay, but we got to talk about it. So I can unconfuse you, Alejandra, if you help direct my questions. So were you confused about the formula? Were you confused about the picture? Were you confused about the units?
I think I'm confused with the beginning of the start of the question, and
let's talk about it. When you say the start of the question, do you mean that you were confused about like the satellite going around Earth?
Yes.
So what I was thinking, Alejandra, when we talked the other day, when we had a one-on-one, wasn't there a lab that you missed?
I did. It was the one with the push pins.
Oh, okay. So you did do the lab with the ISS satellite.
I think I have notes about the satellite, but I
But this is
figured
the
that
exact-
I just needed to.
This is the
What?
exact same problem as the satellite lab. It's just that the orbital height is different. That's how I think about it anyways. I was thinking,
Okay. I was gonna look at my notes, but then I was like, let me try to do this using the sheet. But then when people started answering the questions, I'm like, actually, I don't know how to do this.
well, we're all kind of learning together. That's why we're doing this. So remember, Alejandra, the important thing was that when we looked at the sheet, we were looking for formulas that involve period. And the point that I made to Arunsak was, honestly, there's only 2 formulas that have period in them. So that kind of narrows it down pretty quick. Now, it is up to you to know that the Newtonian version works for any orbits. And Arunsak put it nice and succinctly when he said, p squared equals a cubed only works for planets. Since the satellite is not a planet, we've got to use this one. You also have to know that this requires certain units. That was probably stressful as well. Do you notice that this equation includes the constant big G? Notice that the units of big G are meters, kilograms, and seconds. That should suggest to you that you also want to be using meters, kilograms, and seconds. So that's a trick that I have. Anytime a formula involves a fundamental constant, it's almost always going to require MKS units. That's a pro tip. Okay, someone gave me an answer on chat that looked really, really bad and really, really wrong. So did anyone get a better answer?
I did.
Okay.
I got this, but then I'd
Wait.
round it to like.
I can't really see that, Emily. Can you just tell me what the answer is? Instead of showing, can you say like 1 point something times 10 to the something?
Yeah, I rounded it to 1.3 times 10 to the negative third.
Sorry, you forgot to cube your radius, or you forgot to cube your distance.
Right. Oh, okay. Okay.
Professor,
Yeah.
is there any way you can give us like some more practice problems that we can do?
Yeah, but we got to get through this one. I've got more practice problems right here. I've got another key one. Wait, hold on. What are you saying, Arunsak? Are you saying I'm taking too long?
No, not at all. I'm just saying like after we finish this, I'd still like some more like practice.
Yeah, I'm
Is
at
there
least going to go till 3, and I'm down to give you a little extra too, as long as you guys have the stamina. But we need to move quickly. Guys, why don't we just all punch this together because everyone's getting it wrong. Are you ready to follow along with me? Can you see my calculator okay? You guys can see it? Give me a nod or something, okay? Is this going to work for you? All right. Punch with me. 4
Big
times pi squared times 43 exp6. Now we've got a qubit, which is shift and then this key. Boom. Divided by big G, 7 exp negative 11. And here's another trick. Divided by the mass of the Earth, 6 exp 24. Now we have to hit equals, ba-boom. But now we've got a square root. So I hit shift square root. Okay, Arunsak, what's my answer to 3 significant figures?
86,500.
Okay. Units? What are the units?
Seconds?
Very
No. Oh, okay.
good. How many hours is that?
$24 hours a day.
Hey, I already know better. Did anyone still not get the right answer even when they followed me? I bet some of you still screwed it up, right? Okay, Kaitlyn, do we want to see that again? One more time for the people in the back. Kaitlyn, did I go too fast?
A little bit.
Okay, so let's slow it down. 4, wait, clear out. 4 times pi squared times 43 exp6 shift cube divided by 7 exp negative 11 divided by 6 exp 24 equals shift square root. Did that work better this time, Kate? Okay. Hopefully
I didn't square root it. That's what I did.
okay. Hey, Arunsak, how many hours is that?
24.
I guess that's why they call it a geosynchronous satellite, isn't it? A geosynchronous satellite orbits Earth with the same period as Earth's rotation. So if you launch a geosynchronous satellite, it rotates along with Earth and it will always hover over the same point on the ground. That's how your communication satellites are designed. The satellite always hangs above Rhode Island and you can bounce your radio tower signals off that for like cell phone communications and stuff. By the way, because p squared is proportional to a cubed, putting a satellite at a particular distance will peg it to a certain period. Now listen, in this sample problem, I asked 2 other questions. One was the force of gravity and the other was escape velocity. I'm going to skip over solving those problems because they're boring and you guys can do those on your own. I think we should move on to a different problem. Arunsak?
Yeah, I had a quick question for 2. So I found the formula and there's d squared in the bottom, the denominator. What is d? Is that the radius plus the height?
It's 43 million meters again.
Okay.
By the way, write this number down, Arunsak. Why you? Oh, yeah. Yes, Devin's got a question, and it's an important question. Let me explain what Devin's question is. Devin's question is, hey, dude, there's a times there, so why did you hit divide? The reason why, Devin, is if you hit times, the calculator will think that you wanted the mass of Earth to be on top. By typing divide, you are reminding the calculator that the mass of Earth should be on the bottom. I tried to explain this during the course of our lectures by asking you to compute, Devin, what is 6 divided by 3 times 2? Obvi, if you're a reasonably intelligent person, you should know the answer is 1. But watch, Devin, if I type in 6 divided by 3 times 2, I get 4. Because the calculator first calculates 6 over 3 as 2, and then when you made the mistake of typing times 2, it thinks you want the 2 in the numerator. You can solve this problem by always hitting divide. 6 divided by 3 divided by 2 is 1. In other words, Devin, even though it says times there, you actually have to hit divide to make sure the mass ends up on the bottom. Hopefully that answers your question.
I've got a quick question. You said that for the second problem, the d squared is the 43 times 10 to the 6.
Correct?
Is that like the exact same thing as a, or?
Yeah, it was A in one problem and it was D in another. It's because of the way the formulas are defined. In Newton's versions, Kepler's third law, A is the semi-major axis of orbit, but during the law of gravitation, D is the center to center distance between the two objects. And if one of the objects is a satellite, so what? It's still, the D is, in this case, what was A in the previous problem is now D in the new problem. And that's okay, Emily.
Okay.
By the way, the answer to number 2, you should get around 9 newtons worth of force. And the escape velocity is going to turn out to be like 4,400 meters per second. But I think you guys should work on those on your own. That's not important. What's important is for us to try the next problem because we're running out of time. Is that okay with everyone? Okay, we should move on to a different, yes, let's do it, says Devin. Okay, let me show you another type of problem you're going to have to solve. At least now you know what to expect here. I want to make sure you guys get a wide variety of exposure to the different types of problems you'll be expected to solve. In this problem, we're going to consider a famous star known as Arcturus. I'm going to give you some givens about Arcturus. First, I'm going to tell you the luminosity of the star. The luminosity is 170 times the luminosity of the sun. I'm going to tell you the radius of the star. Oops, no. I'm going to tell you the star's diameter. The diameter of the star is 50 times the radius of the sun. I'm also going to tell you the temperature at the star's photosphere. It's 4,300 Kelvin, just like our sunspot today. I'm going to tell you the distance to the star. The distance to the star is roughly 37 light years. Now, you guys probably don't remember the luminosity of the sun and the radius of the sun, so I'm going to put them up here. The luminosity of the sun is 4 times 10 to the 26 watts. The radius of the sun, I'm going to do you a big solid, and I'm going to give it to you in meters. The radius of the sun is 7 times 10 to the 8 meters. That will let you convert the luminosity to watts and the diameter to meters. Here's what I need from you. Question 1. Convert the distance of the star to meters. That's dimensional analysis. You better be able to do that. Bye, Alejandra. I'll see you at the vegetable market, maybe. 2. Find the brightness of the star as seen from Earth. 3. Find the angular size of the star in units of arc seconds. 4. Find the brightness at the surface of the star. Question 4 is not the same question as 2. They're different questions. Question 5. Find the peak wavelength of emitted light. 6. In what regime is this light? Okay. If you get stumped when you start this problem, ask me for a hint right away. I don't want you floundering. I'll pause until we're ready to work on it. Are we
On
getting
3.
this? You're on 3?
I'm like, you're just starting 3 for me.
Okay. Is anyone getting stumped on which formula to choose? It seems like you guys are working, so I'm just going to let you work a little bit longer, okay? Okay, I want to talk about it. The unit conversion should be pretty straightforward, right, class? Let me speed that one up. 37 light years. You got to go from light years to kilometers. You got to go from kilometers to meters, right? 1 light year is 9.5 trillion kilometers. It's 1,000 meters per kilometer. A little trick that astronomers like to remember is it's 9.5 times 10 to the 15 meters per light year. In fact, why don't you guys write this down so you can use it during the test? Here's a bonus conversion factor that you can write down on your sheet. 1 light year is equal to 9.5 times 10 to the 15 meters. Write that bonus conversion factor down and it'll save you little bits of time in the test. By the way, while I'm at it, there's another really useful conversion factor that I think you should write down. This will help you out many different places. 1 year is 3.15 times 10 to the 7 seconds. That will definitely save you a whole load of time during the exam. Okay, so what do you guys end up getting? You end up getting 37 times 9.5 exp15. That gives me 3.5 times 10 to the 17 meters. Does everyone agree with that?
Yep.
Okay, cool. Okay, what did you do for the next problem, Arunsak?
I got Boltzmann's equation.
Gianna,
Yeah,
it's
I
9.5
think that-
times. Okay, wait, let me address Gianna's question for a second. Gianna, it is 9.5 times 10 to the 12 kilometers per light year. But if you want to go to meters, it's 10 to the 15 meters per light year, right? 12, 13, 14, 15. Does that make sense to you? Okay. Sorry, Arunsak.
Yeah, I picked
Yeah.
Boltzmann's. Is that
Yeah,
the right
that's
one?
what I got too. But no, it's not the Boltzmann equation.
I did that too, and then realized that's for the surface, right?
That's very good, Christopher.
Mm.
At the surface of the star, you can use Boltzmann equation. But Christopher, what do you have to do to find the brightness from Earth?
I have no idea.
Well, there's only one other formula that has B in it. What is it? Emily.
The inverse square thingy, but I don't know what any of that means.
Yes, you do. We did that. Which version of the inverse square law do you need? The one with R or the...
There's only one version on the thing, so I guess that one.
Guys, you need to update your formula sheet. That's my bad. There are two versions of the inverse square law. One of them is brightness is luminosity over 4 pi r squared. Please write this down on the side of your paper because it's important. The other version is brightness equals luminosity over 4 pi d squared. It's honestly the same thing, but one uses distance. Sorry, my handwriting sucks with the mouse. There's the version that has the radius squared, and there's the version that has the distance squared. That's what you want. Let's see what's going on in the chat window. Oh, Devin's, okay, yeah. Well, if you think about it, guys, let me go to my whiteboard for a second. You can still think about it as radius if you want. Whiteboard, share. Check this out. If I have a star there, I can think of it as being surrounded by a big, giant sphere. And I can think of Earth as being over here. Okay. And then you can think of the distance from the star to Earth as d. But you could also think of it as r, the radius of a big giant sphere. So it's the same equation. It's just how you want to think about it, right? Does that picture make sense to you guys? That's the star's luminosity, and the distance or the radius is the distance from Earth to the star. Okay. Okay. Blair, I'm going to tell you something. Blair, wait, did you already answer my question? D squared is the same as R squared. Blair, when you're new at algebra and math and physics, you tend to get really worked up. Does D stand for distance? Does R stand for radius? D and R stand for some quantity of length. In this case, okay, Devin, or Arun, oh, I'm sorry. Oh, sorry, I got confused there. Okay, Arunsak. I know, I'm kind of busting my budget here. Blair, let me just keep it simple in the interest of time. D and R are kind of the same thing. You just have to deal with it, okay? L over 4 pi d squared is how I would have considered it. What units do I want for L and D, class? We should make a GC. What's a GC? Oh, okay. Oh, group chat, okay. All right. Guys, if you're studying and you need some help from me, just let me know. So, do you guys want to see the solution to this? Okay, so let's do that. So first, to find the inverse square law, I've got to find the luminosity in watts and the distance in brightness. So the luminosity of the star is 170 times the luminosity of the sun 170 times 4 times 10 to the 26 watts. If I multiply those, I get 6.8 times 10 to the 28 watts. For the distance to the star, I use the 3.5 times 10 to the 17 meters. Then I plug them into the formula. Brightness equals 6.8 times 10 to the 28 watts over 4 over pi over 3.7 times 10 to the 17 meters squared. Let's punch them up. I get 4 times 10 to the minus 8 watts per meter squared. Is that what you guys got? Emily, Stacy, Christopher? Who else is?
I was writing it down. I'm sorry.
That's okay. You guys should punch that in and make sure that you get that. No, Gianna, you do not need the parentheses. I put the parentheses there for the units, not for the calculator. Gianna, the reason I use the parentheses is because I want to remember that the square distributes to the meters as well as the number, so that my final units will end up watts per meter squared. Did you get this? Okay. Gianna, can I tell you what you're doing wrong? Gianna, you are making the same mistake that Devin was making earlier. Divide by 4, divide by pi, divide. Divide, divide, divide. Try it again. Emily, Stacy, Christopher, will you tell me what you're getting?
Yeah, I got 4 times 10 to the negative 8 too.
Yeah, I got the same thing.
Awesome. Stacy?
I didn't. I'm messing up on the square at the end, but I know I'll work it out.
No, we'll work it out now. Punch with me. You ready? You ready to punch? Hold on. I need light. 6.8 EXP28. Oops. EXP28. Divide by 4. Divide by pi. Divide by, ready for me? 3.5 EXP17. Square that. Now equals. Shit, how did I get a negative? Well, I hit a negative key by in there. Did you get it this time, Stacy?
Yes, I did. Thank you so much.
Killer. Okay. Okay, let's move on to the next one. Angular size of the star. Cool, Ty. I'm glad you're still with us. I forget that there are trolls back there who are still with us. Maybe, okay, well, whatever. Okay, let's talk about the third question. The third question was to find the angular size of the star. Okay, the picture is that the star is over here, and you're looking at it from far away. The angle in arc seconds is alpha. The diameter of the star is S. This is you. You're the observer, which is an eyeball on Earth. And this is the distance from Earth to the star. What formula do I want, students?
You want the, I think it's small angle formula.
Correct, but do you want part 1 or part 2?
Looks like part 1.
False. Part 1 will give you the angle, Christopher, in units of degrees. You want the
Well,
unit.
can't you just convert that though?
You could if you felt like doing extra work. Do you want to do extra work on a 100-point test?
No.
Then why don't we just use this one and then you won't have to convert.
Okay.
But you're right, Christopher brings up a point. You could use either version as long as you keep your units straight. But Christopher, I'd say it's better to use that version, don't you? Christopher, here's the issue. The diameter of the star and the distance have to be in the same units. Okay? We currently do not have them in the same units. In the interest of time, I'm going to convert them both to meters. I know that the distance is 3.5 times 10 to the 17 meters. I'm going to convert the diameter, 50 solar radii, into meters. S is the diameter. 50 solar radii is 50 times 7 times 10 to the 8 meters. 5 times 7 gives us what? 35. 8 plus 1 is 9. Or 3.5 times 10 to the 10 meters. I did that right, correct? Yeah. Okay. So up here, I'll use the small angle formula part 2. Alpha is 206.265 arc seconds times the diameter, 3.5 times 10 to the 10 meters, divided by the distance, 3.5 times 10 to the 17 meters. This is going to leave me with 206.265 times 10 to the minus 7. 1, 2, 3, 4, 5, 6, 7. And my answer comes out to be 0.02 arc seconds. Did you guys see how I did that in my head? I probably lost you there, didn't I? 3.5 cancels with 3.5. 10 minus 17 is minus 7. So I just went back 1, 2, 3. Or plug it into your frickin' calculator, whatever. 0.02 arc seconds. Okay, Christopher, you figured out on your own that question 4 involves the Stefan-Boltzmann law, right?
Yeah.
There's actually 2 different ways to do question 4, Christopher. Question 4 is a choose your own adventure. In question 4, you're supposed to find the brightness at the surface of the star. Method 1, which is the one that Christopher suggested, is to use brightness is sigma t to the 4th because you know that the surface of a star glows from temperature alone. But Christopher, there was another method that we could choose. The other version of the inverse square law, we can calculate the brightness because we know the luminosity of the star. And instead of putting in the distance, we could also put in the radius of the star. I'm guessing method 1 is probably faster, easier, and cheaper, right?
Yes, that's why I used it.
Very good of you, sir. So let's do that. So the brightness is 6 times 10 to the negative 8 watts per meter squared per Kelvin to the 4th times, what was it, 4,300 Kelvin?
Hold on one sec. Yeah,
Punch that up and tell me what you get.
I got 21 times 10 to the 6 watts per meter squared.
21 million watts per meter squared. I like it. That sounds reasonable. How about question 5?
I think that would.
That's to find the peak wavelength, right?
Yeah.
You know what formula to choose for peak wavelength, don't you?
Wien's law.
Yeah, Wien's law. Lambda max is, okay, if Gianna's still there, she's going to want it to be 2.9. But I don't even know if Gianna's still in the background there. Oh, Gianna is. Okay. Gianna, you want to put 2.9? Rock your socks off. Okay. I'm going to just go with 3. 3 million nanometer kelvins divided by the temperature, which is 4,300 Kelvin. What's that give us?
1 second. That is 700
Units?
nanometers.
In what regime of the EM spectrum is that, and what color is it?
I think that would be red.
That's right. It's in the visible regime, and it's the color red. So Arcturus gives off its maximum emission at red light. By the way, Christopher, when you look at the star, because it mixes in a little bit of the other colors, Arcturus actually has a kind of yellowish appearance. Let's go ahead and look up Arcturus.
Isn't it a red giant?
I think it's some type of, yeah. It's only 40 light years away. Let's see what it says. Fourth brightest star in the sky. It's a red giant, yeah.
3 cheers for that one astronomical show I watched on the Science Channel.
They talk about Arcturus?
I think so.
Here's a
I
picture.
watched it in middle school. I don't remember.
Do you guys see how when you look at Arcturus in the sky, how it has like a yellowish appearance? That yellowish appearance is because it peaks in the red, but it's giving off wavelengths. This is kind of like the sunspot question today, isn't it? Actually, Christopher, this is a perfect example of when I said, what color would the sun be in today's lecture? And you said it would be red, and then Cameron said white. And I was like, the answer is kind of somewhere in between, but a little more white than red. This would be a perfect example of that, right? Okay, cool. Okay, we did a lot. There were more questions that we could have done, but let's let it rest there. Is that all right? I think. Yeah, I mean, here. There's one other question I can give you. I don't know if I have the energy to work through the whole thing. Here's one more question. What do you mean? What do you send you the test? Guys, I'm here to help. Hold on. Do you want, you have three options. We stop, I give you another question and we don't solve it. I give you another question and we do solve it. What do you guys want?
I would stay.
Okay, fine. I'm giving you till 3:30. Let's do one more. I'll do one more with you, okay? Because you guys are important to me and this is important to me. So let's do one more.
Thank you.
This problem is about Jupiter and its moon Io. We need to start off by drawing a picture so that you can understand what's happening here. This is Jupiter. This is its moon Io. They are separated from each other by an angular separation of 145 arc seconds. I'm going to give you the period of Jupiter around the sun, and I'm going to give you the period of Io around Jupiter. The period of Jupiter around the sun is 11.2 years. The period of Io around Jupiter is 42 hours. Here's what you're going to do for me. You will, one, find the distance from the sun to Jupiter in AU and in meters. Two, find the distance between Jupiter and Io in meters. Three, find the mass of Jupiter. This will be a cute little problem that will help you. You'll have to do stuff like this during the test, so this will be very helpful. Okay, do you want to take the usual few minutes to see if you can figure it out first on your own?
No.
No, you say just solve it?
Yes.
You just talk our way through. Yeah, it'll be faster that way. Okay. Do you guys have any idea how I would find the distance from the sun to Jupiter?
I would guess some sort of perversion of the small angle formula.
No.
Eh.
There's a simpler and faster way. Let me give you a hint. If you have the period of the planet, you should be able to find that right away.
Newton's third law?
Not Newton's third law. Somebody's third law, but not Newton's.
Oh, p squared equals a3.
Right, don't ever forget about that. P squared equals a cubed. You can find the distance between the sun and the planet very fast. So all you'll do is you'll say A is the cube root of 11.2 years squared. Punch that up and tell me what you get.
Five
5 what?
years.
No, that's not the units that A comes out in.
What's A in?
A is a distance, so it needs to be a unit of length.
I'm gonna guess AU.
Very good. Okay. If Jupiter is 5 AU from the sun, how many AU is Jupiter from Earth?
4.
4 AU. Let's convert that to meters. Okay. To convert it to meters, we'll say 4 AU. AU go to kilometers. Kilometers go to meters. 1 AU is 150 million kilometers, 1,000 to 1. That's 150 billion. 150 times 4 is 600. That makes 600 billion meters. Okay, Christopher, how do I find this distance here between the planet and the moon if I know the distance from Earth and the angular separation?
Could you rephrase that?
Find the distance between Jupiter and Io. How could I do that from what I have? Emily, what do you think? Maybe, but not in this question, Gianna. Guys, you have a distance, you have an angle. You're looking for a separation. There's an elegant, simple formula we can use. You've already used it in this homework session. The small angle formula, Gianna. Part 1, Gianna, or part 2? No, Gianna. Part 1 uses degrees. Part 2 uses arc seconds. As I mentioned to Christopher before, you can tell this one uses degrees because you can see the little degree symbol there. This is the one we want to use because it uses arc seconds. Okay. So let's use the small angle formula part 2. S, the separation between the planet and the moon, is angular size times distance over 206,265 arc seconds. The angular size is 145 arc seconds times a distance of 600 billion meters over 206,265 arc seconds. Let's punch that up together. I get 422 million meters. Verify that you get that as well.
Yes.
Nice. Okay. Guess what formula you're going to want to use for number 3? Question number 3. This is an important tip for the exam class. Find the mass of Jupiter. There is only one formula in all of astronomy that lets you find mass. We've talked about this in our lectures.
1 second.
What is that formula? Anytime you're asked to find a mass, you know this formula is going to be the one. Emily, any thoughts?
So would we be using like one of the equations off the sheet to solve number 3?
Yeah, but there's only one equation. Only one equation that finds the mass. Come on, guys, you can find it. I know you can. They call it the cosmic balance beam. The cosmic balance beam?
Is it one of Newton's third laws?
Newton's version of Kepler's third law, right?
Yeah.
It's the one that's solved for mass. Let me tell you, every time you have to solve for mass, it's this one. We're going to neglect the mass of Io as too small and directly solve for the mass of Jupiter. NK3 solved for mass. We actually have things in almost the right units. First, Emily, can you do me a favor? Emily, buddy? We've got to convert 42 hours into seconds. Can you help me do that?
Yeah, you start with 42 hours.
Yep.
And then the multiplication and the bar. And then minutes on the top and hours on the bottom.
I got a better idea. Do you want to just jump right to seconds? Think about it. How many seconds should there be in an hour?
I think it was like 3,600.
Exactly. It's 3,600. That's a good number to remember, Emily, because there are 3,600 arc seconds in 1 degree. So 3,600 is a good number to remember. It'll save us a little bit of time. Okay, so what's the period then? I get 151,000 seconds. Now we can use NK3 solve for mass. The mass of Jupiter is 4 pi squared a cubed over GP squared. 4 times pi squared times 422 million meters cubed divided by 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 151,000 seconds. What do you get? I'm guessing you're going to get close to 2 times 10 to the 27 kilograms. That's the mass of Jupiter, so that's what I would expect you to get. Oh, wow, we really cooked it today. After this, I probably need to stop because the video will get too long and it'll take too long to render and too long to upload. So in fact, I'll work with you guys for another minute here, but for those night students watching, I hope you made it this far, and I'm going to stop the recording. I'll see you guys during the exam.